Let's jump right into this explainer. Today, we're scaling all the way up from the microscopic forces around us right up to the massive electrical grids that power our entire global civilization. Now, we interact with energy literally every single second of our lives, right? But honestly, we rarely pause to think about the strict physics governing exactly how it behaves, how it transforms, and ultimately, how it gets lost.
Here's our quick roadmap to translate all this abstract physics into real-world stakes. We're going to hit the definition of work, the energy bank account, the rules of transformation, power and efficiency, and finally, powering our world. Let's get to it. Section 1. The definition of work, moving the world. We're kicking things off with a foundational concept that might actually challenge your everyday vocabulary, and maybe even change how you think about the daily grind.
So are you doing work right now? You might think that holding a heavy box for 10 minutes or just sitting at your desk studying hard requires a massive amount of effort. You feel exhausted afterwards, right? Well, physicists completely disagree with that definition. In the realm of science, just feeling tired absolutely does not mean you've accomplished anything measurable.
Here's the golden rule we have to remember. Mechanical work happens when a force causes actual displacement. That's the key. Meaning, if you push a heavy tree with all your might, sweating for an hour, but that tree doesn't move a single millimeter, you have mathematically done zero work. No way around it. Scientific work strictly requires motion.
This perfectly illustrates the difference. Getting paid to guard a building while standing perfectly still at a door, well, that's a job in the everyday sense, but you're doing zero scientific work. On the flip side, pushing an 11-kilogram lawnmower 22 meters across your yard against 86 newtons of friction, now that is true scientific mechanical work. You've applied force and you've created displacement.
Moving on to Section 2, the energy bank account, storing and spending. Now, if work is the action itself, energy is simply the ability to do that work. It helps to think of it kind of like a cosmic bank account, one the universe actually allows you to deposit into and withdraw from. Energy takes on completely different forms depending on whether it's being actively used or saved up. Think of a 60-kilogram skydiver falling at a terminal velocity of 40 meters per second. They are actively spending kinetic energy, which is the energy of motion. Meanwhile, picture a 68-kilogram rock climber gripping a cliff face 320 meters above the ground. They are moving at all, but they are holding massive amounts of stored gravitational potential energy. Basically, they've made a huge deposit into that energy bank account just by climbing up there. Which brings us to one of the absolute most thrilling examples of this bank account in action, a roller coaster. As the cars drop from that initial high point, the coaster is violently trading its stored potential energy for kinetic energy, accelerating you down the track. But then, as it rises back up the next hill, it converts that kinetic speed right back into potential height. It's continuously balancing the energy bank account. And the crazy part is, not a single joule goes unaccounted for.
All right, Section 3, Rules of Transformation, Energy in Disguise. Let's look at how all this builds into an undeniable cosmic rule. Energy never actually disappears, it just puts on different disguises.
Bioluminescent nature executes this transformation perfectly. Just look at glowworms. They're doing something truly incredible, turning the chemical energy from the food they eat directly into radiant light energy. It's literally a flawless biological engine operating right there in the dark.
And humans engineer very similar transformations in our everyday tools. For instance, think about capturing the kinetic motion of turning a crank with your arm. You route that kinetic energy into a device, it gets stored as electrical or chemical energy in a battery, and then ultimately it's transformed outward as radiant energy and sound waves.
A hand-cranked radio like this is a literal lifesaver during natural disasters or power grid failures. It gives us this amazing step-by-step physical connection to the law of conservation of energy. You put the mechanical work in, the device stores it, and then transforms it into the audio and signals that bring you vital news. It's just a really beautiful, highly functional disguise for that energy.
Section 4. Power and efficiency, the waste factor. Now, transferring energy from one disguise to another is never perfect, which brings us to the crucial concepts of power, efficiency, and, well, the catch, the waste factor.
First up, we really have to distinguish between work and power. While work measures the total energy transferred, power measures how incredibly fast you can transfer it. To put that into perspective, think about the explosive crack of a baseball bat hitting a 145-gram ball. That bat is delivering 400,000 watts of power in just 0.70 milliseconds. It's a massive burst of energy transfer happening literally in the blink of an eye.
But here's the thing. Just because a device is powerful definitely does not mean it's efficient. Take a traditional incandescent light bulb. We think of it as a tool for creating light, right? But mathematically, it's really just a heater that happens to give off a tiny bit of light. It wastes an astonishing 95% of its input energy as thermal heat, leaving only 5% as actual radiant light. That is wild. When we compare these everyday machines, the numbers are actually quite humbling. It is shocking to realize a standard car engine is only 12% efficient at converting the chemical energy in gasoline into forward mechanical motion. So the vast majority of that fuel you're paying for at the pump, it's completely lost as exhaust heat and internal engine friction. Even a compact fluorescent bulb, which is an upgrade from the incandescent, only sits at 17% efficiency. Our modern world is honestly incredibly wasteful.
All right, on to our final section, Section 5, powering our world on the macro scale. Let's explode this concept all the way out to the global level and look at how human civilization actually harvests energy from the Earth itself just to keep all these inefficient machines running.
So here we're classifying the absolute backbone of the global electrical grid. We really have to separate the resources that replenish naturally, like biofuel, geothermal, wind, tidal, and solar, from the non-renewables. Those are the finite ones locked deep underground, like coal, oil, nuclear, and natural gas.
But what's truly mind-bending here is realizing where almost all of this originates. The sun is basically our ultimate battery. Surprisingly, whether you're burning a renewable biofuel or a non-renewable lump of coal, you are essentially just releasing different ages of stored sunlight. Think about it. Biofuels are just recent solar energy captured by living plants, while fossil fuels, that's ancient solar energy captured by organisms millions and millions of years ago.
And we gather that solar energy across a vastly contrasting spectrum. Look at this. On one hand, we have a traditional farmhouse utilizing localized, passive solar heat without any complex machinery. But then on the other hand, you see massive industrial extraction of petroleum from places like the Canadian oil sands. Each of these approaches presents completely unique economic practicalities and, of course, massive differences in environmental impacts.
We also have to consider sources that don't rely on the sun at all, like the nuclear option. Conventional nuclear power plants use atomic fission to produce electricity with an incredible energy density. They actually operate at more than twice the transformation efficiency of a standard gasoline vehicle. But it's a massive trade-off, right? This immense power output requires managing highly complex radioactive waste and strictly enforcing environmental safety protocols over incredibly long periods of time. At the end of the day, no matter what source we use, we are permanently bound by the law of conservation of energy. We have to remember that from a tiny apple falling from a tree to a giant hydroelectric dam churning rivers into voltage, the universe's total energy never changes. No device is 100% efficient. Energy is never destroyed, it just transforms into messier, less usable states, which is almost always thermal waste heat just bleeding out into the environment. So I'll leave you with this provocative thought as we wrap up this explainer. If energy never actually dies, but our current tools are so poor at holding on to it, if 88% of your car's fuel and 95% of an incandescent bulb's electricity is just bleeding away uselessly as heat into the air, whoever figures out the technology to recycle and harness all that invisible waste, they are quite literally going to power the future of our world. Think about that the very next time you feel a hot engine hood or a warm light bulb.